Yeah, I can find it.
I'll let you do it.
All right, so I'm going to talk about LADEE operations, but before I start my
Nathaniel Benz.
before I start my presentation, I'm going to play a YouTube video that kind of compares the JPL operations to the LADEE operations. All right, so the first scene, and if you guys don't know, that's Will Wheaton of Star Trek fame. So they're going to compare the reaction to JPL landing on Mars, and everybody's all excited. That's amazing. Look what we did. Yippee. Now let's go to LADEE and Ames' reaction to shortly after launching the vehicle. Spent all this time, 5 years, trying to get this done. There goes LADEE, Q operations, and the flight director in the background. He says, "Nice job, everybody." Yep, that was Ames. Then he makes a joke about us working at Target because we all have red shirts on. All right, so my name is Nathaniel Benz. I don't work at Target. I work at Millennium Engineering Integration. NASA Ames is where I spend most of my time now. I'm going to skip over these slides because we've learned a lot about LADEE, and so I'll refer you guys back to the previous presentations. I'm going to go quickly over an overview of the simulators, pretty much what Danilo just talked about. We have 3 different types of simulators: the workstation simulation, the processor in the loop, and the hardware in the loop. So the workstation simulation, the key point there is that we're running that in Simulink. It's on a typical Linux workstation. And a key point to remember is that simulation is going to run about 30 times faster than real time. Our pill processor is running on flight-like processors. And then our hardware in the loop simulation, these also have the power cards. I think it's interesting to note that a lot of times what people will call a pill in other projects, we're calling a hill here. In other projects, a hill to them would be something that has like the reaction wheels and the star trackers all integrated. So the hill for us is just has the power cards, so we can do hardware commanding. So this is what the WSIM model looks like. We have all the models of the prop, GNC, thermal, along with the flight software done in Simulink. Again, it runs faster than real time, about 30 times faster than real time. What the WSIM doesn't have is the CFE layer. That's where we bring in the pill. The pill has a higher fidelity flight software because it has the CFE layer as well. It runs in real time. It also has ITOS as its interface, which is what we use in operations. And then the hill is one step further. We have all the power cards, so we can do more hardware commands in operations. So like if I want to point to a certain boot slot to run a flight software load, I can do those types of commands. So how do we use the simulators in ops? There's basically 3 areas that we used it in. The tactical cycle, this is when the spacecraft is actually flying. We would upload commands pretty regularly because the science team, they want to be somewhat agile, that they can look at the data and then decide, okay, this is what we want to do today. So pretty much every day we're uploading commands, but before we do that, we want to test the commands and make sure they don't do anything that's going to hurt us. So we would run that through a simulator. The next phase is kind of like the development phase. So this is pre-flight. There's a whole bunch of scripts and processes that operations wants to run. We want to test all of these before we get to the operation phase. We're going to run these through the simulator just to make sure that everything works as expected. And then in the third area is training. Danilo mentioned this a little bit. We want to train all of our mission operators. And I think Doug mentioned that this is pretty much the first time that Ames has done a spacecraft, beginning to end. So a lot of our mission operators didn't have a whole lot of experience. So I think this was pretty important that we had a way to train people. So for the development phase, there's 2 types of products we have. We have an RTS, which is a relative time sequence file, and an ATS, which is an absolute time sequence file. So an example of an RTS, maybe the spacecraft, like the propulsion team, they want to test out one of the heaters. They can write an RTS that would be uploaded to the spacecraft and do a little bit of a test. An ATS is more of like, these are the commands that we're going to be running for a long time, like science operations, power on this, power on that. And then procedures, these would be more, it's not so much commands being set to the spacecraft, but it's testing how the operators are going to react. So, for example, when we have lunar orbit insertion, there's a lot of contingency cases that we would have to have basically in our back pocket. So if the software reboots, okay, everybody switch to procedure this, and we're going to start executing these commands. So to get the flow of the procedures, we would run these actually through the hill with people sitting there and testing them out. So that's the testing phase, so that's pre-flight. This is what an ATS would look like. So there's a bunch of set of commands, and the important thing to note here is that it's a UTC time, so this is relative to the space test clock when we're going to execute these commands. That's opposed to a relative time sequence where it's execute this command this many seconds since the last command got executed. So the next place where we use the simulators was in mission simulations, and I think this is the kind of stuff that got kind of fun for me as the simulation engineer. So we use primarily the hill to train mission operators. So I mentioned before that the interface to the hill was using ITOS, which is the same thing that we're using on the ground to look at telemetry data that come in. So that makes it really easy to train the operators because we already have the interface already set up for us. So mission simulations are, we took the critical phases of the mission. Those would be like launch and activation. So right after spacecraft separates from the booster, the spacecraft turns on and we start doing all of our procedures. That's one. Phasing loops, that was getting to the moon. Orbit insertion, which is pretty much the key event, getting captured by the moon's orbit. And then a typical day in the life of LADEE during science orbit, including a orbital maintenance maneuver. So we'd have a testing campaign that would exercise each of these critical events, and these would be like as flight-like as possible. So if in flight, orbit insertion into the moon's orbit happened around 2 a.m. in the morning, so that's when we ran the simulation. And these would be 24 hours a day, people on console, just like in flight. And Danilo mentioned in the previous talk that we had the ability to inject anomalies, and that's where it got kind of evil and kind of fun for me. Because we get to devise these anomalies to test operators' response. So going back to the flight software development, we had this ability to inject anomalies to test the flight software's response to anomalies, like a switch fail is what happens to, is the flight software going to handle it correctly. This time it's not only does the flight software handle it correctly, does the team correctly diagnose the problem? Can they figure out what's going on? So an example of an anomaly that we created in the launch and activation phase, right after LADEE opened its eyes and says, here I am, what we did on the simulator is we reversed the polarity of one of the reaction wheels. So the fault that we're simulating here is that INT accidentally installed it in backwards, and so it's spinning the opposite direction that the software says, which could happen. So what happened in the sim was you had one reaction wheel spinning up the wrong way than it was supposed to, and the other three reaction wheels were trying to spin up really fast to counteract that. And the net effect was LADEE was kind of just stuck in this attitude with the sun baking in one side and the other side starting to freeze up. This caused the thermal team to get a little bit nervous. We're supposed to be slowly rotating around to keep the temperatures nice and uniform. So we want to quickly diagnose the problem. If it's a software fix, that usually takes a while. So the team's reaction, which was the correct one, was to just power off that bad reaction wheel and let you have three wheels controlling the attitude. It's not as well as four-wheel control, but at least you're spinning and you get out of this critical event. I thought this was really interesting because on actual launch day, the fault management system was a little bit too aggressive. And so it powered off all four reaction wheels. And what happened was LADEE was stuck in an attitude with one side facing the sun, the other side getting cold, which was amazingly like the sim. And some people said, are we actually seeing sim telemetry right now, or is this the actual bird? I think I was probably the only happy person the day after launch because I came in going like, yeah, look at that sim. It's exactly like flight, isn't it? And everybody, you know, I've been up for 16 hours trying to save the spacecraft. So other types of anomalies that we can inject, you know, I mentioned before, causing fuses to blow. We increased the albedo of the moon so that the thermal environment was not exactly as they expected, which was, you know, kind of what they saw. They had to adjust some of the temperature limits that they said they set because the thermal environment was a little bit different. We added a scale factor to the main thruster so that when they did the lunar orbit insertion, the orbit was a little bit off. So they needed to quickly come up with a correction orbit to make sure that you have a good moon orbit capture. So I think that the key takeaway here is that building in that ability to inject faults to test flight software came really useful for training operators during pre-flight. The third area, which we call the tactical phase of the flight, was, okay, LADEE's in lunar orbit. We're going to start doing our science. So there's a very long and basically it's almost like a stock trading thing. Science instruments want to get different time. So there's a big complicated process of how we're going to set up a plan, so this is what we're going to do today. And what I want to point out here is that the last process before commands get uploaded to the spacecraft is this command verification, where we're running a command sequence through the simulator. This shows the workflow of that process. So basically, we'd start off the day, the spacecraft engineering team, they would give me an initial condition. So this is where the spacecraft is today. This would be something like the momentum state is this, the power state is this. I would then run that through WSIM to propagate forward in time to the beginning of the AETS, which is the absolute time sequence, so a sequence of commands. Once this is delivered to me by the mission planner, I run the candidate ATS, so this is what we want to do through WSIM. And so WSIM is going to run, it's going to simulate what the next 3 days is going to be like. And that's kind of an important point that there'd be 3 days of commands that would be uploaded to the spacecraft. So we can't run this in real time, obviously. We're not going to be able to make it in time to upload to the spacecraft. So that's where the WSIM being able to run 30 times faster than real time made this feasible. So WSIM would check out all the commands, mainly focusing on attitude control, flight rules, and spit out a report that says either the simulator or the sequence passes the simulator, or if there's any flight rules failed, then I would reject it. I'd send it back to the mission planner, which usually involved, you know, working with the spacecraft engineering team to say, why can't we do this? Or the science team saying, can you do something different? Or in some cases, we just accepted that we might violate a flight rule that, you know, it wouldn't be that big of a deal. There's also this state right here whenever we have a maneuver. So we had to do frequent maintenance maneuvers because we were in an equatorial orbit. So the moon is pretty lumpy. So you have to frequently update your orbit or else you're going to crash. So I'd say maybe once a week we had to do a maintenance maneuver to change the orbit. And whenever we do a maneuver, we want to run on our highest fidelity sim. So I mentioned before that the pill has a higher fidelity in the sense that it has the entire flight software running, including CFE. So whenever we run a maneuver, we run that on the pill. I don't want to run the entire sequence because, again, that's 3 days. The pill runs real time. So I'd use WSIM to propagate the state forward to the beginning of a maneuver, run the maneuver sequence, which is about an hour, on the pill, and then, again, you know, check the similar set of flight rules to make sure that everything's going to work out okay. This is just an example of what a flight rule looks like. This is one of LDEX's flight rules. So before we go into this, there's 2 ways that you can check a flight rule. There's what we call a static flight rule checker and the simulator, which is a dynamic flight rule checker. So one of the flight rules was you can't send more than 12 commands to the flight software within a single second. I can check that with a static flight rule. I just, you know, see how many commands, 12, okay, that passes the flight rule. I don't have to run a simulator to do that. There's other flight rules, like the LDEX one, that says I can't be I can't point LDIC's field of view at the sun while it's powered on, or else it's going to damage the instrument. So the dynamic simulator comes important in that sense, because there we're modeling the position of the sun, we're modeling the attitude of the spacecraft, and so WSIM will tell me whether LDIC was powered on and the sun was in view, or it was more of like a safe state. So that's an example of a flight rule that can only be checked with a dynamic flight rule checker like WSIM. Some examples from flight of how we use the simulator. Pretty early in the mission, we noticed that the star tracker wasn't really behaving as expected. So what this top flight, or top two charts, this is actual flight data. And these big spikes in the attitude, so that this side right here would be the attitude and attitude rate. So we weren't expecting these big spikes. And what happened was you'd eventually get a spike that was larger than the limit checker. It says, no, you can't roll that fast, so I'm going to send you into safe mode. We used in order to debug this anomaly and figure out what was going on, we eventually determined that, well, the GNC team determined that the star tracker was giving a little bit delayed measurements, and so it would, instead of sending a quaternion at the timestamp that it was expected, it'd be a little bit late, and so the state estimator thought that it had rolled pretty aggressively, and so it sent it into safe mode. So what we did is we went back to the models, to the Simulink models in WSIM. We were able to modify the model of the star tracker to reproduce these big spike events, and so that at this point, we could say, okay, we understand the problem. The benefit here is, since we're using WSIM to debug the anomaly like we did in flight software, it's immediately available operations, because that's what we're using to check flight rules. So any new sequence after we've recovered from safe mode that we upload, we can run it through the simulator and say, are we going to run into any of these bad case events? I don't think I mentioned it, but the trigger for the bad case events is when a big bright object came into the field of view, so like the Earth or the Moon. So we understand the problem. We can check it in the future, and while that's going on, the GNC team can come up with a fix for it. So they updated the estimator to compensate for this unexpected event, and we can go to the operations manager saying, look, we understand the problem. Here's the proof right here. We can fix the problem. Here's the proof right here. And this is the way that we used the simulator in flight to debug anomalies. Another case that I found interesting was near the end of the mission, we had a long lunar eclipse. So LADEE was never supposed to fly through this eclipse. We were supposed to crash in the moon before it happened, because everybody long before said we don't have enough power to survive it. We don't think the thermal environment will be able to survive it. But we got to this point and we said, maybe we could do it, so let's give it a shot. So we got permission from the operations to do an engineering test of flying through this eclipse, because the LADEE, the common bus, had never been flown before. We wanted to really see what the limits were. So before we went into the eclipse, the thermal and the power team did their analysis using their tools. And so what happened was the thermal team says, this is what the temperatures are going to be. And based on these temperatures, this is how long the heaters are going to be on. And so here, power team, this is how much power the heaters are going to use. So the power team then puts that into their tool and says, based on these inputs from the thermal team, and the other attitude, this is how the sun's going to be pointing the entire time, we think the spacecraft's going to be okay. It's not going to reach this limit in the battery temperature, where if it goes below that, the flight software automatically starts turning things off to preserve energy. So after the eclipse, we're still going to do some science. So one thing we don't want to do is risk the science instruments. So this instruments all have heaters, and they have to stay above a temperature. So it's pretty good that we don't, flight software doesn't turn these heaters off. When we did the run through WSIM, it did predict that we would go below this battery limit. But before flight, we kind of agreed that the thermal team has the highest fidelity model, so we won't. We'll accept this risk, even though that WSIM says it's going to go below this limit. And it's important to keep in mind that we weren't supposed to do this eclipse. It's all pretty much an engineering test anyway, so we're okay doing a little bit of risk at this point in the stage. So what actually happened was that the voltage limit on the battery did get exceeded, and that happened within 15 minutes of the WSIM prediction. And I don't want to say that the thermal model in WSIM was better, because it's not. The temperature models were actually better in the thermal prediction. The problem was that they had an out-of-date heater set points from what was actually running on the flight software. So the heaters were on longer than they expected to because the turn-on times were out of date. They also made an assumption about there being a constant battery voltage. And I guess like the point I want to make here is the fact that WSIM had this multi-domain models in here. We didn't have to make that many assumptions. So we had the current running flight software, so we knew that all the heater set points are correct. We had a battery model so that we didn't have to make the assumption that it would be a constant battery voltage. And that is the reason why it gave a better prediction of where the battery voltage would be. So the multi-domain models has a benefit. All right, so some of the conclusions. Having that design environment, so designing the flight software and the sim in the same Simulink environment, I think was a big lesson learned. I think that was a very positive experience, as opposed to having like the thermal model run their predictions and their own tools. We all have one tool that we're running. The fact that we could take the Simulink code and automatically generate C code to produce the pill and the hill, that meant that mission operations had these simulators just ready to go. They didn't have to do their own work to produce them. Using the ITOS interface as the interface to the pill and the hill, that also made things a lot easier for INT and for operations. Injecting faults, building that functionality in the flight software development creates a natural transition to training mission operators. And the fact that WSIM can run 30 times faster than real time made it a viable tool to test 3 days of commands. Some future work that I want to do, if someone is willing to pay for it, a more regular comparison of the flight data and the simulator performance. We built the simulator to be reusable code, but everybody says that their code is reusable code, so it's not really reusable until somebody actually reuses it. So another mission would be to actually test how well we did of creating reusable code would be great. And I think Danilo mentioned that we froze Simulink on 2010B, which is pretty old. So we've already pretty much updated to the modern Simulink. There's new features that we can take advantage of that will be good. That's it.
Can you, well, is there a reason that you decided not to use CFE in the WSIM simulation?
Yeah, so CFE is all C code. What we would have to do is create an S function to import that, and it seemed like more work than it would have been worth. I mean, we could generate code to run on these pills, and that would be just as good. So during LADEE, CFE was still pretty much in development. I mean, the LADEE mission paid Goddard to do some more updates to CFE, so it was possible. It's probably more effort than the benefit would have provided.
All right, thanks.
Do you keep a library of all the models you're building?
Yes, and that's another thing that I would love to release this as like an open source. There's battles going on with lawyers, so
we will be in touch.
Yes.
Because you're going to win.
Yes.
No, there's a lot of people want to help you win. Any other questions?
I think on slide 22, you mentioned that your model of the thermal system had correct set points, but the domain experts' models didn't have the right set points. How did you come to have the right information, but the domain owners had the wrong information.
Yeah, so, there's a database that controls what the set points are. And the flight software reads in that database. And the WSIM model is the same environment where the flight software is developed. So whenever there's a change to the flight software, WSIM has it, because it's the same environment. Why the thermal team thought that it was something different, I'm not sure. I mean, maybe they submitted something and didn't get pushed up. I mean, it should have been caught in thermal vac testing or something like that.
So I guess the database of information, do all the domain owners make contributions to that database, or does it get collated by systems and incorporated?
Yeah, so the way I understand it is that the system engineers goes to the thermal team and asks for its set points and then puts it into the database, and the flight software team pulls that database. And is that correct, Karen?
Yes.
Yeah.
Any other questions? Very good. Thank you very much. Okay, this actually winds up the workshop. You guys did great. This was, I think, the most successful one we've ever had. So I want to thank all of you. I want to thank our sponsors and all the participants and all the presenters. I think you guys just did an amazing job. Thank you very much. I really